Welcome back. This is where the file system stops being a mystery and starts being a tool you wield deliberately. Linux presents itself as one clean tree rooted at /, but underneath it's a patchwork of separate file systems stitched together at mount points. And knowing which directory lives on which device is the difference between a 5-second decision and a midnight outage. In this lesson, we'll walk the FHS layout, lock down production fstab options, dig into disk usage with NCDU and friends, and cover the failure mode that catches everyone once. Plenty of free space, but writes still fail. So let's start with the map itself, the File System Hierarchy Standard. Think of it as a contract. Every top-level directory has a defined job, and Ubuntu honors it. The split that matters most in production is between what the package manager owns and what you own. apt runs the show inside Maj USR. Don't fight it there. Your custom binaries belong in opt for vendor drops like Splunk or JetBrains, or USR local when you've compiled something yourself. And keep an eye on var, because that's where logs and service state pile up and quietly eat your root partition if you didn't carve it off as we did back in the LVM layout. And that's exactly why we carved var off as its own logical volume back in lesson 1. Picture the failure mode. Root hits 100%, and now apt can't write, PAM can't log you in, system can't even rotate its journal. You're locked out of your own box, reaching for a rescue console. With journalctl isolated, that same runaway log flood just stops writing. The system stays up, SSH still works, and you fix it in 60 seconds with journalctl vacuum or a live lvex tend, pulling from the free space we deliberately left in the volume group. And don't wait for the disaster. Alert at 80% in Prometheus and handle it on your schedule, not at 3 in the morning. Now, once those volumes exist, fstab is what actually wires them up at boot. 6 columns deciding what mounts where, as what, and with which options. Always referenced by UUID, never dev just sta1, because device names shift the moment you add a disk. The 2 options you want everywhere: no time, which kills pointless read timestamp writes and is pure performance with 0 downside, and errors, shock remount row, which flips a failing file system read-only instead of letting it corrupt under load. Layer no dev, no suid, and no exec on tmp, home, and var log to shut down a whole class of privilege escalation. And one rule, no exceptions. After editing fstab, run sudo mount a and check dmsg before you reboot, because a broken fstab means the box doesn't come back up, and now you're driving to the data center. So those are the rules. Here's the daily workflow. Start with Feynman T for a clean tree view of what's actually mounted. lsbulk-f shows you the block devices and their file system types side by side. For a quick test, mkdir and mount Sean devs db1 manually. Nothing persists, perfect for poking at a new disk. To make it permanent, grab the UUID with belkid, append the line to fstab, then sudo mount a to validate before you ever reboot. The remount trick is the one people forget. Mount O remount, no time, no dev, home changes options live, no unmount needed. Ideal for testing. And when umount says target is busy, lsoft plus d tells you who's holding it. Umount L is your lazy fallback, but treat it as last resort, not habit. Now, when Majot var hits 90% at 3 a.m., you need a workflow, not panic. Start with df-h for the big picture, then df-i because inode exhaustion looks identical to full disk. We'll dig into that later. For the y, NCDU is your daily driver. Install it once, point it at var, and navigate visually. When you need something scriptable across a fleet, the -esh on wash var star pipe through sort gives you the top offenders in one line, and find catches the specific monsters, files over 500 megs, or runaway logs touched in the last week. The real win, though, TDF output to a trend log weekly. A snapshot tells you you're full. A trend tells you when you'll be full. Once you know how to find the bloat, you need to know where it usually hides. And on Ubuntu, it's almost always one of these 8. The system journal grows unbounded by default. Vacuum it to 500 megs. The apt cache silently hoards every .deb you've ever installed. Docker is the worst offender on container hosts. Prune images, containers, and volumes together. Snap keeps old revisions forever unless you tell it to retain just 2. Old kernels pile up in boot and will wedge unattended upgrades when that partition fills. The rest, user caches, crash dumps, stuck mail queues, are smaller, but they're exactly what bites you at 3 a.m. Wrap all 8 in a monthly script, and crucially, alert when reclaim returns 0. That silence means something is stuck, and stuck is a different problem entirely. Now here's the failure mode that ruins careers. df-h says you're at 60%, plenty of room, but every write returns no space left on device. You're not out of space, you're out of inodes. On XT4, the inode count is fixed at format time, so a runaway mail queue or a session directory with 500,000 stale PHP files will exhaust the table while blocks sit empty. The fix is df-i to confirm, then find pipe through awk to locate the offender. Usually postfix, mail drop, or an unevicted cache. Delete by mtime to recover, and long-term, either reformat with -N for more inodes or migrate to XFS, which allocates them dynamically. And this is why, when we get to Prometheus, you alert on both metrics. Most people only watch space, and that's exactly how this one hides. Shifting gears from disk to memory, TMPFs lets you mount RAM as a file system, and Ubuntu already does this for you. Run find-menti-t TMPFs, and you'll see /run/dev/srm and your per-user XDG directory all living in memory. The real wins come when you opt in. Enable tmp.mount and /tmp becomes scratch space at memory speed, or carve out 8 gigs for a CI build cache, and watch apt upgrades run 5 times faster than on SSD. The catch is that TMPFS counts against RAM the moment data lands in it, so cap your total allocations at half of physical memory and alert at 80% utilization. Because when TMPFs fills, writes fail, and the killer starts hunting processes. Now for the war stories. 5 file system gotchas that have ruined real weekends. Number 1 is the fstab typo. Edit the file, reboot, and you're staring at emergency mode at 2 in the morning. So always run sudo mount-a first, which validates syntax and tries the mounts without committing your boot to them. 2 ties back to inodes from earlier. df shows space free but writes fail because you've exhausted inodes. Check both -h and -i and alert on both in Prometheus. 3. Snap quietly hoards old revisions at nearly a gig each, so set refresh.retain to 2 and prune the disabled ones. 4. Add NOAA time to your mounts and reclaim roughly 30% of wasted I/O. There's genuinely no downside. And 5. When df and du disagree, it's deleted files still held open by a process. lsof pipe grep deleted finds them. Kill the holder, space comes back instantly. Pulling it all together, you've picked up 6 skills that form your storage foundation. You're fluent in the FHS layout and know why USR is off limits. You can write a production fstab with UUIDs and sane error handling. You've got a safe mount workflow using FindMint and mount-a. You wield the df, incdo, do Trinity for disk analysis. You monitor inodes alongside bytes, and you know when TMPFs earns its RAM budget. Next lesson, we shift gears into bash productivity. History search, parameter expansion, pipe fail, and the 10 commands that genuinely run 95% of ops work. And that's lesson 4 in the bank. Storage understood. You've got the 4 pillars locked in: FHS layout, fstab and mount, disk analysis, and the inode and TMPFs nuances that catch most people off guard. Next up, we move from file systems to fingers on keys. Bash productivity, the skills you'll actually use every hour for the rest of your career. Load up lesson 5 when you're ready. See you there.